All right, welcome to video 8. This video, we're going to be focusing on the graphs of the other trigonometric functions. So far, we have only talked about sine and cosine as functions, but we can extend those main ideas to the remaining four trig ratios, tangent, cosecant, secant, and cotangent. So to start, what we're going to look at is tangent. And we're going to look at it in terms of it being a function and in terms of x, that being my input. And so what I'm going to do though is I'm going to look at my input specifically in terms of these special angles as we were to go around the unit circle. So if you have a copy of the unit circle, or I would encourage you to get that out, or if you're watching this video, pull up a full unit circle copy and follow along as we go through. Because when I go through and I evaluate tangent, if I want to evaluate it, remember that tangent is the y-coordinate over the x-coordinate from the unit circle. And this again is why the unit circle is so important. And that's also why I want to make sure that we're not confusing this x here with the x in this definition. When we're dealing the ratios and when you're looking at the unit circle, the x and y and its association to sine, cosine, and tangent are only that. So when I turn and I start looking at now function notation, my x represents, again, the input into this function. My x now is going to be a specific angle instead of going through and listing out theta, etc. All right, and so my x, as you'll see in the table below that, I have all the values ranging from 0 to 2 pi. And let's just go along and find tangent of each angle. If you want to go through and fill out this table or create this table on your own, I would encourage you just to pause here. Then using the unit circle, go through and construct y over x and go ahead and simplify it. That's what I'm going to do as well. All right, and so I'm going to go ahead and start now. Going into 0, when I do tangent of 0, this is going to give me an answer of just 0. This will be 0 over 1. When I go to pi over 6, this is where we're going to have the radical 3's, and so we're going to have to just be careful as you're going through and doing this. All right, so here I'm going to get 1/2 divided by root 3 over 2. This is 1/2 times 2 over root 3, or 1 over radical 3, which is radical 3 over 3, like so. So there's my pi over 6. Pi over 4, this is where x and y are the same coordinate. All right, so that means when I construct tangent, this will be radical 2 over 2 divided by radical 2 over 2. This is going to give me 1. And then for pi over 3, this is going to be radical 3 over 2 divided by 1/2. Well, this will be radical 3 over 2 times 2 over 1, which is just radical 3. Notice that pi over 3 for tangent is essentially the reciprocal of this value. Now, pi over 2 is where it gets interesting. So I'm going to go ahead and clear these out. Because at pi over 2, the coordinate there is 0, 1, meaning when I create my tangent ratio using its definition on the unit circle, this is going to give me 1 over 0, which is undefined. Right? I can't divide by 0. So this means that tangent actually does not exist at pi over 2. There's not a point there for pi over 2 like there was for sine and cosine. And so literally the graph will never cross this vertical because there's no point that will connect it to anything else. And so this is going to be something that's really important to kind of remember, especially as we complete the table, but even more so when we come back and we look at the graph, which we'll do in a minute, as you see kind of below this. All right, continuing, so when I go to 2 pi over 3, this is where we can use the idea of reference angles to kind of help us here, because I know 2 pi over 3 will have the same answer as pi over 3. So I know that this has to be radical 3. But this is going to be negative because tangent is negative when I'm in the second quadrant, which is where these next couple angles will come from. Remember, essentially, the trick, this was from essentially a week or so ago, that it's all students take calculus, and this is telling me where and which trigs are positive. So all of them are positive in the first quadrant, only sine is positive in the second, only tangent is positive in the third, and only cosine is positive in the fourth. So because 2 pi over 3 is in the second quadrant, then this answer will be negative radical 3, which means when I get to 3 pi over 4, this will be the same answer as pi over 4, which was 1. But again, because I'm in the second quadrant, this is negative to be consistent even in how I draw it. 5 pi over 6 will be the same answer as pi over 6, but again, negative because of where I'm at. Now at pi, again, this is going to be an interesting one because my coordinate is 1 over 0. When I go through and do tangent, this is going to give me 0 over 1, which is 0. Right? I can do 0 divided by anything, that's fine. And so that's why here at pi and here at 0, we actually get answers unlike pi over 2. All right, continuing. So at 7 pi over 6, this is going to give me the same answer as pi over 6. And because I'm in the third quadrant, this answer is actually the exact same answer. It's going to be positive radical 3 over 3. So if we're kind of following this pattern, and notice that these angles here are essentially mimicking these exactly. So it'll be radical 3 over 3, then 1, then radical 3. And then at 3 pi over 2, remember this coordinate here is 0, negative 1. Tangent will not exist here because, again, this is going to create a, this is going to create a 0 on the bottom of a division problem, which I cannot have. So because I can't divide by 0, the graph doesn't exist. It can't be drawn there at 3 pi over 2. It creates, again, this invisible force field. The graph can never touch it. And then continuing, this will be negative radical 3, then negative 1, negative root 3 over 3, and then I'm back at 0, which is the same point as 2 pi. So therefore, tangent of that is 0. And then we know from talking about sine and cosine, essentially this table here mimics the graph everywhere else. So if I wanted to keep going after 2 pi, then I could essentially go back to the beginning and then keep counting and again follow the bouncing ball. We'll be able to continue in doing the sketch. All right, so what I want to do is I want to plot this, but I want to plot this in, essentially as a lazy man. And the way that I'm going to do this is essentially looking at my table. This is easy to graph, this is easy to graph, this is easy to graph, this. Essentially, I'm going to graph all of the zeros and pi's. So here. I'm going to do all of the over 4s and any of the over 2s. Right here. And you'll see I've already actually marked these on this graph below. And so I'm going to go through and plot this then. I'm going to use blue to kind of mimic this. So at 0, tangent is 0. At pi over 4, I was 1. And then at pi over 2, this graph does not exist. So graphically, what I get then, and what we've seen before, is this is a vertical asymptote. There's an invisible barrier here that the graph will never touch. And then if I was to sketch, the graph will look something like this. And we'll confirm this on Desmos in a minute. It's almost like half of a quadratic. All right, now when I come over here at 3 pi over 4, I get negative 1. At pi, I get 0. At 5 pi over 4, I get positive 1. And then I repeat with another vertical asymptote at 3 pi over 2. And so to sketch this, what it actually looks like is something like a cubic. At 7 pi over 4, we get negative 1. At 2 pi, we get 0. And this essentially, we can continue sketching because this pattern would just continue. Essentially, it would look just like this little piece here, over and over and over and over. Now, because though it's kind of centered or kind of off center, the part that we're actually going to focus on is this part here, which would be represented by negative pi over 4 to negative pi over 2, which would create another vertical asymptote. In this image, I'll try to do a rough sketch as best I can. Something like this. And then I can essentially just copy and paste this over and over and over to continue the graph, and I'm not going to fool with it too much. And so essentially tangent then would be constructed like so, and we'll kind of confirm this in Desmos. I've already got this set up with the pi's. I will type in tangent x, and then you'll see all of the waves over and over and over. To better see where the vertical asymptotes were, recall we had one at pi over 2. So I'll put in that x is equal to pi over 2. We had another one at 3 pi over 2. We had one at negative pi over 2. And so what I want to ask is, where would the next one be in either direction? Like, how would I essentially find that? Is there a pattern to all of these in terms of my asymptotes here? Well, you guessed it if you're looking in terms of what I'm showing here. Because of the pattern and because of the symmetry, the next one would occur at the next over 2, which would be 5 pi over 2. The next one would occur at 7 pi over 2, and then 9 pi over 2, and then 11 pi over 2. Essentially, we can then come up with a generic expression for it. I know I'm going to now have vertical asymptotes for tangent at pi over, let's see, x is equal to pi over 2, wouldn't erase, plus repetitions of pi, where k is an integer. Now, what this is essentially saying is if you're looking at the distance here between pi over 2 to 3 pi over 2, this is the exact distance of one single pi. And that makes sense when you're looking at this and saying that this is essentially a half, and this is essentially 3 over 2, or 1.5. The difference is exactly one whole unit, specifically one whole unit of pi. And so this gives me essentially my starting point to start counting, and then this is the way that I would count. So if I only wanted my very initial first vertical asymptote, I would let k be equal to 0. And you notice this expression would then say pi over 2 plus 0 times pi, which is just pi over 2. If I wanted the next one, I could let k be equal to 1. And then I could go through and say pi over 2 plus 1 times pi. Well, this would be 1.5, or 3 pi over 2. If I wanted to get to the next one, I would let k be equal to 2. Well, this is doing all of the vertical asymptotes starting at pi over 2 and counting to the right and getting all of my positive angles. Well, if I wanted my negative angles, I would start at pi over 2 and move to the left by subtracting and using negative values for k. This would be positive values. And that's why it says k is an integer. And so this is how we can start expressing an infinite amount of angles, is by writing it in terms of an expression like so, where we use this variable k to count essentially for us. Because sine, cosine, and tangent and their reciprocals are periodic, that means all of these special attributes, these characteristics, happen at specific intervals, that interval being its period. And so if we're paying super close attention then to this idea of a period, what would the period of tangent be? Well, if you're looking at the graph, remember period stands for the length of one repetition. Well, one repetition can be viewed as just this one cubic-like sketch, because that's the copy that gets repeated every time. And then if I'm counting, notice that this is 1/2 of a pi from here to here. This is another 1/2 of a pi. So period for tangent is 1/2 plus 1/2, or 1 pi. This is the period. And so again, in the vertical asymptote expression, you'll see that it's pi over 2 plus k times the period, which is pi, because that's how long it takes to hit the next one, and then the next one, and then the next one, whether you're moving in the positive direction or the negative direction in terms of adding and subtracting with k's. All right, now, this is just talking about the period, and it's talking about the vertical asymptotes. So what about the domain? What am I allowed to actually plug in here? Well, the domain for tangent is all real numbers. In other words, you can choose any x that you want to, but x can't be any of these vertical asymptotes. So we say that x can't be this expression, pi over 2 plus k pi, where again, k is an integer. I can use any other x. This again is what's called set notation. It's a way to give out a list of x values. If you wanted to use interval, you would say, I don't know, it'd be a little bit trickier, wouldn't it? Because you would have to do essentially parentheses and brackets for every single thing. I guess you could almost do it in terms of words. You could say all real numbers except, and then you would say x can't be pi over 2 plus k times pi. And that'd be for the domain. What about the range? So the range again is the range of outcomes, right? What are the outputs? What are the y values that we can achieve? Well, unlike sine and cosine, notice that there is no floor and there is no ceiling, meaning that when I look at this graph, I can actually hit every possible y value. Range is actually all real numbers. Or negative infinity to infinity. We can actually get any single answer from doing tangent. And we can achieve that by picking radian measures that are getting closer and closer and closer to a half of pi, or any of these vertical asymptotes, because the graph is forced to continue moving up or down, since I can never touch these vertical asymptotes and touch these barriers, but I have to continuously get closer and closer to them. Okay, so this is the graph of tangent. This is the vertical asymptotes. This is really just to kind of get you familiar with the graph. We're not going to do too much with it. All right, so this leads us essentially then into cosecant. And cosecant is a little bit different from tangent. We're not going to really fill out a table. And it's the same thing when we get into secant and cotangent because of their relationships to the big three. Cosecant, for example, is specifically 1 over sine. All right, it's the reciprocal, meaning flip. So let me add that in. So what I want to do is essentially, let's look at the graph of sine. All right, so I'm just going to put up just a basic graph of sine. You'll notice that I kind of have a basic graph set up right here. I've highlighted just the main 5 key points for a sine graph that's not been transformed. So this means that sine would start at 0 in the middle. At pi over 2, I'd reach my max. Back to the middle to -1, back to the middle, and we just continue to alternate as the cycle continues over and over. Sorry, my nose, it just, all right. So same thing, moving to the left, back to the middle. All right, so I'm just going to do a rough sketch as best I can with this. It's not going to be perfect, but it is something. I rotate my iPad when I do this. Helps me get the curvature just right. Okay, there's one side, and there's the other. All right, and so this is the graph of sine, and we know this continues on and on and on. And what I want to do now is with this basic function here, I want to focus on these points where specifically sine is 0. All right, so if I go through and I was to say, you know, what is sine of 0? The answer is 0 because that's the y coordinate there at the unit circle. All right, if I say what is sine of pi, it's the same answer, right? Sine of pi is 0 because that is the y-coordinate at pi. Well, what if I went through and I asked you for cosecant of pi? Well, what this is telling you to do is to find essentially 1 over sine of pi, right? That's the definition that we have here. Well, this is just telling you to take that y-coordinate of pi and to flip it, to reciprocate it. But the issue is at this specific value, sine is 0. And 1 over 0, like we saw with tangent, does not exist. So that means graphically, at each of these x-intercepts, so I'll do this in red. At each of these points where I cross the x-axis, it means that cosecant does not exist. So it creates vertical asymptotes at 0, pi, 2 pi, 3 pi, on and on and on and on. 4 pi, 5 pi, 6 pi. But not only to the right, but also to the left. So negative pi, and then negative 2 pi, negative 3 pi, etc. Well, to finish the construction for the graph of cosecant, it's this idea again of being a reciprocal, right? Focus here at where sine is at its maximum. So if I was to go through again and ask you to evaluate, and I said, what is, looking in the top left, what is sine of pi over 2? You would say 1, right? That's the y-coordinate of pi over 2. Well, if I was to say, what is cosecant of pi over 2? The answer is still 1, because that is the reciprocal of 1, right? 1 is trivially, is defined as 1 over 1. So flipping it, it's kind of redundant, right? It's trivial. So there's no like really big thing to do here. So what that's telling us is that cosecant and sine share a point. It shares these maximum and minimum values with one another. And then if I think about what's happening when I do a cosecant, when I think about this idea of reciprocation, this flipping idea, these vertical asymptotes act like scissors. So imagine that I'm literally taking my sine graph and I'm cutting it along here. So I'm creating these little individual horseshoes. And then to finish cosecant, I'm literally flipping these horseshoes. So this one would get flipped up. This one would get flipped down. This one would get flipped up. This one would get flipped down. Obviously, it would have another half. This would get flipped down. The next one would be at 1, and it would be flipped up. So the next piece would look something like this. And so these green horseshoes, these individual ones in between each of the vertical asymptotes, this is the graph of cosecant. So let me erase the sine piece. And so this is the graph of cosecant. And what I just walked you through is actually the process to graph cosecant. What you would do is you would rewrite your problem in terms of sine, graph your function in terms of sine, and then everywhere that everywhere that your graph hits the middle, in this case the x-axis, you would draw your vertical asymptotes. This would literally cut up your sine graph, and then you would flip each piece in the middle to create the graph. Now from this, let's go through and just talk about some important characteristics. Let's start with the vertical asymptotes themselves. Notice that cosecant has vertical asymptotes everywhere that sine is equal to 0. Well, that happens at 0 plus every pi afterwards. So I represent that as saying k times pi, where k again is an integer. And so this means that if I don't want to go anywhere, k is going to be 0, and my first vertical asymptote would be at 0. Let me say x is equal to. If I want the next one, I would say k is 1, and I would get 1 pi, then 2 pi, then 3 pi, etc. So this means my domain then is all x's but x just cannot be one of these vertical asymptotes. And notice I'm not going to do the 0 plus because 0 plus is, again, trivial. I don't need to write it. All right, well, what about the range here? Because the range is actually pretty tricky. All right, my range, notice there is no graph here to here, right? There's nothing in between, and I'll draw a black line here, right? If I notice, the bottom of these horseshoes hit at 1, and these horseshoes hit at a peak of -1. There's literally nothing in between. But if you recall, that's where the original sine graph was, and that's why, because everything's been flipped out of this little no man's zone. So I need to write this. Well, if I'm thinking about range again, range is floor to ceiling. So because of the arrows, these graphs continue infinitely down. So my floor is essentially negative infinity up to -1. Union 1 to infinity. Notice how these intervals here don't include anything in between -1 to 1. Makes sense because there's nothing here in between -1 and 1. So let me get rid of these. All right, and so this is all the information for cosecant that we need in terms of its graph. I'm not going to ask you to graph cosecant. A couple of things that I am going to do with cosecant, though, is go through and essentially evaluate certain values. And you've done this practically already, but just to give you another example of this, what if I asked you to find what is cosecant of, pi over 4? So something like this. Using the unit circle, you'd go to pi over 4, and its y-coordinate is radical 2 over 2. But because I'm doing cosecant, I'm flipping the y-coordinate. So I'm flipping this to be 2 over radical 2, which again is 2 radical 2 over 2, or just radical 2. All right, and so being able to do this, we've talked about again already. This is roughly about a week and a half ago. I want to say it was the Friday before last, so the 17th. That doesn't sound right, but maybe the 13th. I can't keep all my days straight. No, that's not right either. All right, whatever. One of those. All right, so go back and review that if you need to. I'm going to go to Desmos now, and just like how I showed you tangent, I do want to show you cosecant. So I'm going to erase these. Ooh, excuse me. All right, so I'm going to do cosecant of x. And you'll see here the humps, the horseshoes. And notice again how these horseshoes, though, are being contained inside of the pies. And so if I was to go through and mark x is equal to, I'm kind of interested. Let's see if this will work. Hopefully this won't freak you out. If it does, I'm sorry. Let's put a k here, and then a pi. I was hoping it was going to let me do a thing. Let me see if I can do a pi. No, it's not going to let me add a slider. So let's just do x is equal to, 0. Red's a terrible color. So there's one vertical asymptote. We know we had another one at pi. So there's another vertical asymptote. Then another one's at 2 pi, etc. I guess one last thing to talk about with this is what would a period be? All right, because this again is a periodic function. In other words, how long does it take for one complete cycle? Well, one cycle needs to consist of one horseshoe going up and one horseshoe going down. And notice that would take from 0 to 2 pi. So the period for cosecant is the same as sine, 2 pi. They have that in common. The only major change here, again, is because we're reciprocating, you're taking the original function for sine and you're literally flipping it. That is how we construct for cosecant. All right, now the next one to look at is secant. This one's going to follow the exact same pattern that we just did with sine. So just as a review, secant is 1 over cosine. And just like how we constructed cosecant by going through and graphing sine and then cutting it and flipping it, we're going to do the same thing with cosine. So cosine at 0 starts at 1, starts at its max, and then goes to the middle. It's min, middle, it's max. We've completed one period, but let's keep going. And the same thing to the left. And then just to get a rough sketch, here's the graph of cosine. This graph again, of course, would continue. All right, we know everywhere that this graph is 0, secant does not exist. So that means at negative pi over 2, there's a vertical asymptote. At pi over 2, there's a vertical asymptote. 3 pi over 2, etc. Anywhere that cosine is 0, secant will be undefined, because that would put a 0 in the denominator, which again does not exist. And then like last time, we're going to treat these vertical asymptotes, these lines, these vertical lines here, as if they're cutting. And then I'm going to flip this graph. So the reciprocal 1 is 1. It would then flip directly up, flip down, flip up, flip down. And this process would continue. All the way on the far left, flip down. And so secant looks very, very similar to cosecant. It's just been shifted over. We can go through and write the equations for the vertical asymptote. They happen at every single pi over 2. And notice they repeat every pi. So very, very similar to tangent. Notice the period for this is the same as cosine, which is 2 pi. Now this might be a little bit harder to see just because of the way the graph is cut. But notice one period would have to take essentially from peak to peak, or one horseshoe going up and one horseshoe going down, and that distance here is still 2 pi. And you can look at it in terms of this distance here, or even starting at 0 and going to here. This essentially gives me the right half, this gives me the left half when I go through and do these. So the period is still the same. My domain, writing it in terms of set notation, it's going to be any single x, but x can't be one of these vertical asymptotes, so no pi over 2's. And then my range, like with cosecant, would go from negative infinity to negative 1, where that's included, union 1 to infinity, just like cosecant. So a lot of similarities between the two. To go and look at Desmos for this, plot secant. Very, very similar graph to cosecant, though the main difference again is that my vertical asymptotes are different. They're at every over 2. So there's pi over 2. Here would be negative pi over 2 if I wanted to go the other direction. And then this part would continue. So here's my vertical asymptotes. All right, now let's say, for example, you were given a problem, and that problem said to sketch the graph of 3, let's say secant of 2x minus 1. And let's say this was your problem. Now, if you were to sketch this, again, the process would be to really go through and sketch 3 cosine of 2x minus 1. So these problems are actually just hidden modeling questions that you saw last week, again. And just to kind of justify that, what I'm going to go through and do is just type this into Desmos here, just so we can see what the graph is, and then type this in and see if what we did before actually works with this and works with this process. So let me go to Desmos. Again, we had y is equal to 3. I'm going to do the cosine, so cosine 2x and then minus 1. Notice my amplitude here is 3. I have a midline at negative 1. And I have an amplitude of 2, meaning I'm getting more frequencies here. Now, what I want to highlight is, like we did last time, I'm going to zoom in here. I want to highlight all the points where I'm not at the x-axis now, but where I'm in the middle, and that's one of the key differences between this and what we did before. So these pieces here. So pretty much all of the over 4s. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And I'm going to put these in as vertical asymptotes. So I know I have a vertical asymptote at every over 4. So pi over 4, I'll make this dotted. I'm in the middle at, the next one is 3 pi over 4. Again, let's make this the same color and dotted. We know we have another one at 5 pi over 4, green and dotted, and then another one at 7 pi over 4, and this will make one normal cycle, so we'll end here. And so what I would expect then is that this graph would be cut along these vertical asymptotes, and then each horseshoe here would be cut and flipped. All right, so let's type in the version with secant. So y is equal to 3 secant of 2x minus 1. And you see that exact thing. So when we're graphing secant, when we're graphing cosecant, replace that with the general sine and cosine and follow the general methods that we've talked about. After you do that, then the process by hand is by finding where is this function in the middle, where would it zero out with itself, which happens here. And there's my vertical asymptotes, and then we cut and flip. Now, because this is the process, I'm not going to ask you any questions to sketch secant or cosecant, or even cotangent or tangent. Tangent's pretty important, just in the sense of its inverse, which is what we're going to get into in the next video. But in terms of actually being able to recreate the graphs, it's just a redundancy of doing sine and cosine. So I'm not going to require you to do any of that. But I do want you to refamiliarize yourself with, again, what is secant and how we find it, cosecant, etc. The last one I'm going to show you in Desmos, which is the graph of cotangent. And then I want to highlight specifically its domain and range. Its vertical asymptote, like the formula for the vertical asymptotes, and its period. Now, just as a reminder, cotangent is the reciprocal of tangent. So anywhere that tangent is equal to 0, cotangent would be undefined. And anywhere that tangent is undefined, cotangent is now 0. And that sounds pretty trippy. But essentially the reason why is because anytime that when I'm solving tangent and I originally got 1 over 0, cotangent tells me to flip that. And it now becomes 0 over 1, which is legal. Anywhere that tangent was 0 over 1, tangent tells me to flip it, and now I get something that's illegal. So cotangent actually becomes the same idea. It's just a flip and a shift of what tangent looked like. All right, so I just want to graph cotangent. I'd encourage you to do this as well in Desmos and just kind of play around with it. So here is cotangent, and it looks like this. Very, very, very similar to tangent. So let me put this in just to trip you out. So here are both of them. Here is tangent. So notice how it's essentially increasing from left to right. Cotangent decreases from left to right because it flips it. Not only that, if you remember, tangent crosses at pi's and zeros. Well, look at where cotangent does not exist at, pi's and zeros, because that's where my vertical asymptotes are. So my vertical asymptotes for cotangent occur at every 0 and every pi. Thus, k times pi. The period, because we're basing this off a tangent, is pi. The domain would then be all x values, but x cannot be a vertical asymptote. And then my range would be all real numbers, like when we looked at tangent. Because again, going back to Desmos, I can hit every single y value. I can zoom out. You'll see that this graph would just continue on and on and on. All right, so that's it for the other 4 trig functions. They're not as important when it comes to modeling, which is why we didn't really focus on them at all before until now. But I wanted you to be aware of them. So you'll see some practice problems, really just kind of working again on evaluating with these reciprocals, in tangent again, as well as I might give you some sketching for secant and cosecant specifically. It'll just give you some extra practice for graphing sine and cosine. So I encourage you to try those. Use Desmos to kind of double check your work, but again, just doing rough sketches for these. All right, that's it, and I hope you have a good rest of your day.